So in the last class, we have learned some close relation between symmetry and conservation laws. You will learn in group theory that if there is symmetry, you can apply group theory. That is all, they are also closely connected. So the symmetry during the translation or rotation in space and time, that leads to the conservation laws which are familiar to us. So the reason for this is very interesting idea. The reason for conservation laws, which are the important factor of our physical science, conservation laws. So these are basically due to the symmetry and isotropy of space and homogeneity and isotropy of space and homogeneity of time. So next we are going to consider so all the three previous operations transformations are continuous transformation. Now we are going to consider two discrete transformation. So first we are going to do space inversion. This may be already known to you. Usually we call it as parity operation. You change x to minus x, then what happens to the function? Then if the function, nothing happens to the function, we call it as even parity. And if function changes sign, that is odd parity. This is known to you. So here also we do the same thing. We change x to minus x. If it is one dimension, you change x to minus x. So this is a discrete transformation. Don't think that when you change from x to minus x, it goes to x positive x decreases, then reaches 0, then reaches minus x. It is not like that. So when you do this operation, immediately x changes to minus x. There is no in between states between x and minus x. Okay, so that is why we call this as discrete transformation. So space inversion is a discrete transformation, and if you do the in 3 dimension, if you do the space inversion, x becomes minus x, y becomes minus y, and z becomes minus z. So actually what happens is this is like a mirror reflection, or we call it as reflection symmetry. Mirror reflection. Okay, so it is like you look at the mirror. When you move away from mirror, you image also moves away from mirror. So when you look at mirror, if it is same, we say that there is a mirror symmetry or reflection symmetry. Actually, what we are doing is space. We are inverting the position coordinate. That is why it is known as space inversion. And in 3D, if you do all the x, y, and z to minus x, minus y, minus z, what happens is actually in 3D, if you change all the axes to minus, when you do the mirror reflection, when you do the space inversion, what happens is the left-handed system converts into right-handed system. Okay. Or if it was initially a right-handed system, then it becomes left-handed system, and vice versa. Okay. So if it after reflection, so I think you know what is left-handed system and right-handed system. If you rotate a screw through the right hand, what happens? Or if you rotate through the screw with the left hand, what happens? That is the difference between them. Now, if the system becomes invariant after reflection, invariant, no change under space inversion, this implies a reflection symmetry. Or we can say mirror symmetry, or another technical word is parity is conserved. We say reflection symmetry. Another technical word is parity, no change for parity, or parity conserved. So after reflection, if nothing happens to the system remains invariant, then we say that conservation of parity. Another term usually we use is, if parity is conserved, we say the system lack chirality. System lacks chirality or chirality, or we say chirality means the handedness, right-handed or left-handed, handedness. That is chirality. That is a property of the system. So these are the usual thing. Now let us see what happens under parity operation. When you do parity operation, what happens to the dynamical variables? Under parity operation, the position vector, what happens to position vector? Position vector r changes to minus r. Okay, x, y, and z all changes. So vector r changes to minus vector r. Now what happens to the velocity? Velocity is dr by dt. Velocity v equal to dr by dt. So what happens to it? Since r is involved in it, that becomes minus dr by dt. So velocity changes sign. Position coordinate changes sign. Velocity changes sign. So since velocity changes sign, momentum also changes sign. Vector p becomes minus vector p. But you notice that the angular momentum, what is angular momentum? L equal to r cross p. L equal to r cross p. Is there any change for angular momentum? Because r becomes minus, p becomes minus, momentum also both changes sign. So L becomes invariant. So there is no change for L. Minus r cross minus p equal to L itself. No change for angular momentum sign. Sign of angular momentum. So L is conserved. L is conserved. Means no change for L. So all other things are changing its sign, but L remains unchanged. Now, as before, let us find the parity operator. Who can do this parity operation? The parity operator you can call it as U unitary P, UP. Okay. So UP is the operator. Why the name U? Because it is unitary. Unitary operator can do anything. So UP is the parity operator. Okay. So this can be defined as use this above previous properties. Okay. So what happens to the how the operators can be transformed under a unitary transformation? So suppose operator is R, position vector R. Okay. Then you do the similarity transformation or by a unitary operator or a unitary transformation on R. That is U, P, dagger, then UP. UP dagger, UP. At center R. Okay. This will be after you do this unitary transformation, R becomes new R. New R, what is new R? That is minus R. R changes sign. So you can call it as R dash, R dash, R prime. So new R prime is minus old R. Okay. So this way you can define the unitary operator. And one more thing we know, P dash, new momentum operator is UP dagger P UP. That also changes sign, so you can put it as minus P. So you can find an operator which has this kind of properties. So that operator can define the parity operator. So naturally, this R and P, they should satisfy the Heisenberg's commutation relation because both are changing sign. So no problem. They satisfy Heisenberg's commutation relation. Okay. So immediately I will try to give some physical concept regarding this. Suppose consider a one-dimensional case. Suppose the particle is here. It was moving in this direction. Okay. So you do the parity operation. What happens? Immediately, this was its initial position. R becomes minus R. So immediately particle reaches here. And what happens? Momentum becomes negative. So the particle tries to move in the opposite direction. Okay. So initially particle was moving in this direction. Immediately after parity operation, particle, this is discrete transformation. So the particle cannot exist anywhere here. Immediately it reaches here. Then momentum becomes negative. This is what actually happens. Okay. For a moving one-dimensional system. For other system, it is slightly complicated. Now, nothing happens to a scalar. For any scalar operator, that will be S operator, scalar operator. So these are vector operators. Now scalar operator, there is no change for scalar operator. S dash equal to UP dagger S UP. Okay, which is equal to no change for S, same as S itself. Okay, so scalar operator, no change. So S dash and S are same. So from this, what is UP? S dash and S are same. Okay, so you UP and UP, therefore UP dagger UP. This should be 1 for UP to be unitary. So this can be written as UP dagger, which is the definition of unitary operator. So the unitary operator you can define as UP dagger equal to, as we did in the last topics, you can define this one as e to the power of I delta. Okay, e to the power of I delta. Delta is a very small quantity, and this you can write it as 1 plus x, like that you can expand. So UP dagger you can write it as e to the power of I delta, then UP. So if you choose like this, all these will be satisfied. Okay, so if you choose like this, what is UP? What is UP? You multiply on both sides with UP dagger UP. Okay, so you get, from this you can or you can do one thing, you multiply with e to the power of minus I delta on both sides on the left side. So here it becomes 1, so you can write UP equal to, multiply with e to the power of minus I delta. So here it becomes 1, so here it becomes e to the power of minus I delta UP dagger. Okay, you multiply with e to the power of minus I delta here and here, left side, on both sides. So here it becomes 1, here it becomes e to the power of minus I delta. So if you choose like this, they are related, UP and UP dagger are related. Then if you substitute this one here, it will be, all these relations will be satisfied. Okay, so you can choose the unitary of, you can check that, you can see that if you define like this, instead of UP dagger you put this, instead of UP you put this. So all these relations will be true. Okay, so UP is the operator capable of doing this parity operation. Okay, so if you choose like this, what UP becomes actually Hermitian. You take the dagger of this one, so you get the previous one. Okay, so you take the dagger of either this, then you get this one, or take dagger of this one, you get this one. So UP becomes a Hermitian operator. Okay. Now, for simplicity, let us write UP operator as P operator. P. Simply P represents the parity operation. You can put that also. Okay. Because UP generates this P, or P generates UP. P generates UP. So P also can be written for parity operation. Okay. Now the question is, when P acting on wave function, what happens? Okay. So P, therefore, P acting on psi of R, what happens? As a result, what happens? R becomes minus R, psi of minus R. Okay. Suppose once again P is acting. This is the effect of P. So suppose P is acting once more, P square. Again P is acting here. So P is acting, that means P is acting psi of minus R. So that becomes psi of R. Just like an involution. So again, if you do parity operation 2 times, system returns to its initial state. Okay. So eigenvalue of P square is one. Okay. Therefore, eigenvalue of P is plus or minus 1. Okay. So plus 1 means even parity, even or positive parity, means no change of sign. No change of sign. So plus positive eigenvalue corresponds to no change of sign. Minus 1 means odd parity or negative parity, means sign changes. The sign of the function changes or wave function changes. Okay. So this after a parity operation, if the system remains invariant, or the Hamiltonian remains invariant, the system needs some definite parity. So every system needs definite parity when, if Hamiltonian is invariant under parity operation. Okay. So this is a very important idea. System, most of the microscopic system, we will, especially in particle physics or like that, we always tries to check the parity of what is the parity of the system. So in nuclear physics or particle physics, we an example is that, I will tell you an example. The weak interaction, which is the case of beta decay. weak interaction violates, which is the beta decay, which is the beta decay. Okay, this process violates parity. Okay, so beta decay violates parity operation or parity conservation. Violates parity conservation. So this is using this property. Actually, you can identify the presence of beta rays. Okay, if you do the mirror image, okay, parity is not conserved, so you can beta rays you can distinguish using this parity operation. If you take the mirror image, it will not be identical. So this property you can use experimentally to detect beta decay. Okay, parity operation. Now an operation is odd operation if P A P dagger, or you can put the reverse way, is minus A, odd parity. Okay, so this actually leads to the anti-commutation relation A comma P. So that you can easily show that you multiply with P on the right side, then you take everything together. That is an anti-commutation relation. So odd parity leads to the anti-commutation relation, and the even parity operation is even if P A P dagger equal to A, positive parity or even parity, and that leads to the commutation relation A comma P. Okay, so these are the some of the ideas. So parity operation leads to the power or the discrete transformation in space is x changes to minus x, known as parity operation. Okay, so that leads to some of the useful results, like in beta decay. You can experimentally detect that by comparing the mirror images with original images. Okay, so that is another conservation law, parity conserve. So it is important to always check the parity conservation during the atomic and subatomic processes. Okay, now I will continue after some 10 more minutes. I will start a new session. So then I will complete the parity, not parity, time reversal also. Okay.